All right, the next thing we have is 16.3, which is conservative vector fields. We did mention what a conservative vector field is. We defined it in 16.1. So as a recap here, what a conservative vector field is, so a field capital F is conservative there exists a function, which we call a potential function, or a scalar potential, such that the gradient of this function f, let's go ahead and give that f over there, there we go. So a field capital F is conservative if there exists a function f, a scalar potential, such that the gradient of this scalar function is that vector field capital F. So essentially, what we're saying is a vector field capital F is conservative if you can find another function so that when you take its derivative, I know that this is the gradient, but the gradient is a type of derivative. So, in other words, conservative kind of means antiderivative. Can you find a function whose derivative is this function? So in this case, in this sense, little f, the potential function, is sort of a multivariable antiderivative because its derivative, the gradient, is that vector field. Quick remark, we'll come back to this after we talk about this Theorem 1. That's going to be our priority, and then we'll just do a quick little backtrack here. So Theorem 1 is really the big result for this section. This is the fundamental theorem for conservative vector fields. So we're going to assume that capital F, our vector field, is the gradient of some scalar function f. So what this is really saying is that the vector field is conservative, i.e. capital F is conservative. So if it's conservative, and let's say that R is a path along a curve C from point P to point Q in some domain D. So let's say we have a path here. It starts off at some point P and works its way in an orderly fashion to the point Q, the end. So P is our starting point, Q is our ending point, and this is the name of our path C. So if we take the line integral of, over this path, of some vector field, so imagine we have some vector field f. So there's our vector field capital F. So we're integrating over a vector field from a point P to a point Q. If this vector field f is conservative, therefore it's the gradient of some scalar function, then really there's like a equal sign kind of in between here. We can think of this as first being equal to this, and then that's equal to that. You don't need to do this little intermediate step here, but it is what's happening here. I like to write it like that because this right here is much more reminiscent of what you learned in Calc 1. So for a moment, let's come down here and think about Calc 1. In Calc 1, you learned the fundamental theorem of calculus, which is if, let's go ahead and say, if the derivative of some function g is some function f, then the integral of the derivative of g with respect to x from some beginning point A to some ending point B, then this is just g evaluated between the endpoints, which means g of b minus g of a. More concrete example here is the integral of 2x dx between 3 and 4, let's say. Well, we know that the derivative of x squared equals 2x. So we can say x squared between 3 and 4 and get 16 minus 9. It's because this is an antiderivative of that. Well, that's exactly what's going on up here. We're really saying, let's go ahead and make this a little bit bigger. If the gradient of little f equals big F, then the integral over c f dot dr has to be exactly the same thing as, we can just replace f with, right, if these two things are equal, we can swap this for the gradient of little f at any point, dot dr. And this is sort of the same setup. This is saying derivative of this thing. Similarly, derivative of this thing is this thing evaluated at the endpoints. So this thing evaluated at the endpoints. So if this path begins at P and ends at Q, then this would be f of Q, the endpoint, minus f of P. This is really no different in the fundamental theorem of calculus. The notation's just extended a little bit. All right. So that's nice. If you're integrating over a conservative vector field and you know or can find a potential, then instead of doing all the evaluations that we did by evaluating like this, instead, we can just figure out a potential function and then plug in our endpoints. Sometimes this is easier. Yeah. Put it this way, it's a lot easier to do a problem if your answer only depends on the endpoints but not on the actual path itself. So, that's exactly what this is saying. In particular, the line integral of a conservative vector field is path independent. The actual path doesn't matter, only where you began and where you ended your path. Anything can happen in the middle, just as long as you end and begin at the same point. Then the answer is the same. So here's where the next notation comes in. You'll see this little circle here. And this circle is really essentially telling us that this path C is a closed path. So if we look up here at remark number 1, this is saying that a path is closed. A path being closed means that the endpoints are connected. So that's closed path. Circle's a closed path. Maybe something that loops underneath of itself. That's a closed path. Anytime the endpoints are the same, that means your path is closed. And if your path C is closed, then that means you can, if you so choose, you can put this little red circle in the middle there. And that communicates to the reader that this path C is closed. So if we take this idea down here, if this vector field capital F is the same as the vector field up here, in other words, this vector field is the gradient of F, well, if our path, if the beginning and endpoints are the same, then this means P must equal Q, in which case this would be F of Q minus F of P, but if P and Q are the same thing, that has to be 0. So what's nice is the circulation around a closed curve is always 0 if your vector field's conservative. If your vector field's not conservative, that does not have to be true. So that's the big takeaway here.